T is a normal operator. Okay. And S is some operator which commutes with the ST equal to TS. Okay. Then S of F of T, it commutes with F of T also. Okay. Whatever the L infinity is, there is an L infinity in the background, and there is a mu corresponding to that, and it commutes with R of that. Okay. So we were in the middle of proving this. So to prove this, it's enough to prove S commutes with all spectral projection. Okay, because we can approximate any function by simple function, so we can approximate any operator by linear combination of spectral projections, sequence of linear combination of spectral projections. So, and commutativity is preserved under that conversion, so we can do this. So to prove that it's invariant, it commutes with all spectral projections, it's enough to prove that it leaves the space of the space invariant. It leaves the space of the spectral projection and its orthogonal complement invariant. But the orthogonal complement of its spectral projection is again a spectral projection. It just corresponds to the complement. I mean, spectral projection is some 1ET. The orthogonal complement of this 1E complement. It is precisely that. You can, because this plus this equal to 1. And it is just another projection which adds up to 1, which is just 1 minus P. So because of that, that is true. So because of those reasons, which I have already said, I believe, in the last class, this is equivalent to saying S leaves all spectral, also all spectral, spectral projection invariant. By this I mean it leaves the subspace invariant. It takes it. So we have taken this all those E in Fourier sigma algebra of C, such that S of this range of 1 ET is contained in one range of 1 ET. Okay. So then we proved the following. We proved any disk, any open, closed, or something. Initially we proved a unit disk is there, unit closed disk is there. So then first we proved any closed unit disk is there. Unit disks are contained. Unit disks are contained in this. Okay. Unit disk is closed unit disk is there. Okay. Then we proved that any open. Then we proved that any disk is there, any closed disk is there, because that is just the translation. That x minus the center divided by r. That you will bring it to that. It's contained. It's in there. It is in there. Oh, any closed disk. Okay, is in there. It's fine. Okay, then we proved it's closed under, this is closed under increasing union, decreasing intersection. So this is because if some sets increases to some set E, then the corresponding projection will also increase. That's because projection will the projection will also increase. If some E1 is contained in E2, then the corresponding projection is contained in that. That's because you can take the 1 E2 minus 1 E1, which is equal to 1 E1 minus E2 minus E1. So because of all these things, it will follow. Okay, so because of that, that's also so the projection is also increasing. Okay, that corresponds. The difference of the projection is again a projection means one is contained in that. Okay, so the projection also increasing, and in particular they converge strongly because here the 1E, the corresponding indicator function will converge strongly, so that converges strongly. So because of the increasing union, the same reason for decreasing intersection also. So because of that, any closed disk, Because of that, any open disk, everything is there. Okay, so this implies any open disks are also there, also contained in that. So after that, what do we do? So once we prove that open disks are there, then we want to prove what? Hmm. So we use the Helmholtz theorem for that. I mean, for the first one, D, and then using that we got all these things. So then I think this will imply this disk will imply any open half plane, either left half plane. I mean, you take a line. I mean, you take something greater than a real number A, that will give you the right half plane, and something less than a real number A will give the left half plane, and imaginary part greater than something will give you the upper half plane. Then similarly, the now all these things, the proof is same. We proved for the right half plane. So from disk we got the right half plane. So any half plane is contained is half, all half planes, okay, either left or something. Half planes are contained in this. Okay, and finally this is F is closed under finite intersection and finite disjoint union. I mean, in fact, infinite countable disjoint union is also true, but finite is enough for our purpose. Countable disjoint union, because we want to show something is an algebra, and then from that algebra property we want to use monotone class. We have already seen it's a monotone class. It's increasing union, decreasing intersection is there, so it's already a monotone class. We just have to prove. We just have to get an algebra which generates this, and then we have to prove that that algebra is contained in this. Okay, so it contains an algebra that we have to prove, and to prove that we need only finite intersection, finite union, but countable disjoint union is also. Okay. So countable. So why is this true? That is because if you take finite intersection, so if you have some E1 up to En, then the one intersection Ek is same as the product of one Ek. Okay. So now the product, if you apply the corresponding T here, this will become the product again T here. So this is, but this will just, so this is, but then this is just the intersection of all the projections. Intersection of the range of the projection. So range of this is the intersection of range of this. Okay, I mean the product of projections. If you take n projection, then the product of projections when they commute with each other, of course it has to commute. These projections commute with each other. Then the commutative product of commuting projection is just the projection onto the intersection of the range. So this I think I gave it as an assignment. Okay, so because this intersection of the range of one ek. So because of this if ek is there, then the intersection is also there. Okay, I mean if something leaves all the projections invariant, then it leaves the intersection also. Right? Each you can see that. So similarly, if it is disjoint union, that's also true. I mean, any union you cannot take for projection, because union of two projection is not a projection, even if they commute. You have to take orthogonal projection. Okay? Even if it may commute with, it may be something like this. You have a projection which is like this. Then you can take part of this and part of this. Okay, part of some subspace here, part of some subspace here. That will commute with this. But then if you take the sum, it will not be. On the other hand, if you take something in the orthogonal thing, then if you add, it will be again some one somewhere, and then if you take orthogonal projection, if you have two orthogonal projection, then the sum is again a projection, and it's an if and only if statement. Okay, if you have two projection, their sum is a projection if and only if they are orthogonal to each other. Of course, if they are orthogonal, they will commute with each other. Okay, so because of that, so if you have disjoint E1, if you have maybe countable, you can take. There is no difference. Countable you can take. The disjoint collection, then what happens? So then one of intersection En, union En, disjoint union En, is just summation one En. Okay? If it's just clear, so if something takes one something is, this function takes the value 1 if and only if it is in one of them, and if and only if it is equivalent to one of them. And if it is in one of them, it will not be in the other one of them. So that's why this is the sum. It's clear. Okay. So this, as functions, this is true. Now the projections corresponding to this one, this E and T, the same as the sum will be preserved under this. So this implies the projection. I mean, so now this is just the projection onto the range of the union of one E and T. Not union, union closure. Not even union. I mean, these are all orthogonal projection. You take the, you should say direct sum. Direct sum of one union. Okay, direct sum, maybe I'll put the range inside here. This is equal to n. This is equal to the projection onto the direct sum of n, range of one en. Okay, I believe these things are clear. Okay, I think I gave some of these things as assignment. So from that it will be clear. So because of this, we know that disjoint union is there, and then finite intersection is there. So now we consider this algebra that A equal to all those things, AB cross CD, okay? Finite union. Finite, do we need disjoint union or finite union? So finite, but finite union can be written as disjoint union. No? Finite union. This kind of sense. Okay. So I mean, and the another thing is in the half plane. Whenever I said half plane, left half plane, right half plane, upper half plane, lower half plane, it's included you can include the infinity also. You can take the whole all of them also. Okay. Now this AB CD is just you take the this is right half plane, open right half plane, then cross intersection, left half plane, maybe the closure. I think the closure is needed, no? No, it's not needed. You can take LB, which is just all those things greater than here, but you need the closure. Then only you will include the plane. And similarly, you take the upper half plane, upper C intersection, lower B. I think it's fine. Okay. So we know that finite intersection is there, and then finite union, disjoint union of these things is also there. But notice that any such thing, any union can be written as disjoint union, and the complement is also there. See, in general, if you take a complement of this kind of set, that will be A complement cross B union A complement B complement union A complement cross B complement. It will look like this. Okay. So all those sets look like this. Possibly there will be an infinity in this B ABCD can be infinity somewhere. Okay. So if we take the complement, then that will work. Okay. So this says that A is an algebra. All these things says that A is an algebra. Whatever the argument we have done, this implies A is an algebra, and it is contained in this. Okay. And we have already shown that script F is monotone class. So by monotone class lemma, this is sigma algebra. F is a sigma algebra and equal to this. I mean, that's A also generate A. I mean, this is Borel sigma algebra generated by open disk, of course. So you have much more than that. So this is a sigma algebra. Okay. So this is proved. So what I have proved, we have proved Fourier's theorem, which in particular says that if S commutes with T, then S star also commutes with T. S commutes with the T star also. Okay. So now I want to go to the next one, which is the several families of normal operators. So now how many people are there? The same 6. Okay. So you take the consensus. I will do this today. I mean, I don't want to give this as an assignment. I mean, leave this for presentation. So I will do this today. Okay. So what is it we want to do today? We want to consider the joint spectrum. We want to consider the joint spectrum for a commuting family. So several commuting family. Of normal we have to see, but I will take self-adjoint itself. I mean, it will see any normal operator is actually given by two commuting self-adjoint operators. Okay, and that will give the theory. I'm just wondering whether to. I mean, this is general theorem. Maybe for finite thing we have done, and from that you can directly deduce the finite statement for finite family for general normal. But this is a general. This is a general statement for any family. Okay, so let xi be a family of commuting self-adjoint operators. Okay. So then for any, so let for any f contained in a finite set. Okay. This is the joint spectrum, which you have already defined. I mean, all those lambda 1 up to lambda n, which admits a joint approximate eigenvector. Joint spectrum of xi in f. This is a finite family, which we have already defined. Okay. So now we want to define the joint spectrum for this infinite family, possibly infinite family. Okay. So to do that, we need the following lemma. For it to be well defined and for it to be a nice compact object and things. Okay. So the lemma is the following. So we have this projection uh, f from this I to you take the direct product of sigma of xi. Okay. It's a topological space. They are all compact space. Okay. It's a topological space, compact topological space. It's a direct product. Tikhonov's theorem says that this is a compact space. Okay, so do this direct product of the sigma of xi, maybe j. Okay. So this is just a direct product of finite family, and from here to here you can have the coordinate projection. This is just the coordinate projection. I mean, this is an infinite tuple. You just take the tuples corresponding to this finite family, and that's the coordinate projection. Okay? And similarly, you can define from some EF. Okay, so this is if E contains F. Okay? E is a bigger set. From that you can define the coordinate projection. This is also coordinate projection. I mean, it's not coordinate projection. It's correspond to those coordinates, the finite coordinates. Okay, coordinate. Or you just call it the projection. Okay? You just take the tuple correspond. I mean, tuple correspond to this is E. For sets in E, then you just take the corresponding coordinates in F and then project it on. So that's a well-defined projection. So now the lemma is the following. So we know that this joint spectrum corresponding to, I mean, we know that sigma E is contained in this. Okay. Similarly for F. Okay. So the statement is, if you have E and F acting on sigma of E, then you will get sigma of F. That's all. Okay. This is the statement. Right? Statement is clear? Okay. So to prove that, let us prove it when the set differs by only one element. Okay. So assume, I mean, we want to use induction. Okay. So we assume E and F differs by only one element. So the cardinality, this is cardinality, this modulus is cardinality equal to. So when that is the case, we prove it. And then it follows from n to n plus 1 we have to prove, and we will apply this for n to n plus 1. Okay. 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 So why is this true?
Like,
So,
are you asking E to be finite?
yes, E and F are finite. I mean, we have defined this sigma E only for finite sets. So we want to define it for infinite set. For that, we are doing all these things. Okay? So E and F are finite. So assume this difference, this cardinality of this set difference is 1. Okay? Okay. So what do we have to prove? We want to. Okay. So let. Okay, we just take it to be 1. E, let E equal to 1 up to k plus 1, and F equal to 1 up to k. You can just write it like this. Okay, and some operator, let's not take k plus 1. So what do we have to prove is, we have to prove that if we apply that projection, we get precisely this. So given anything, we have to get an image from that. I mean, given this tuple lambda 1 up to lambda k in this sigma F, okay, we want something there. There's some lambda 1 up to lambda k and lambda k plus 1 in sigma E. Okay, then the projection will be precisely that for some lambda k plus 1. So we want to choose that lambda k plus 1, and we know where to choose. It has to be in the spectrum of the remaining one. So let lambda k plus 1 is in the spectrum of xk plus 1. Okay, we basically take I mean, we have, see, the earlier we did something that is different. There we took lambda k plus 1 and we showed that there exists a lambda 1 up to lambda k such that the combined tuple is in the bigger spectrum, bigger giant spectrum. Here we are doing something slightly different. That's all. Okay. Okay. But we are doing the same thing. The idea is same. Okay. So the idea is let us consider the projection. Notice, so we want to take a set. So what is that set called? So let epsilon greater than 0. See, earlier for epsilon we took some interval in epsilon neighborhood around this lambda k plus 1. Earlier around this lambda k plus 1, and we considered the projection corresponding to that. Then we took the eigenvector in that space and did something, and that satisfied the whole thing. Here we are going to do for this tuple, and then we want to get a giant eigenvector. This tuple as a joint eigenvector because that is in sigma f. Okay. Now for this lambda k plus, we want to get the same with the same joint approximate eigenvector. We want to show that that's also lambda k plus 1 is also an eigenvalue. Lambda k plus 1 is also an approximate eigenvalue. Okay. Let epsilon greater than 0. Okay. And then consider the projection. Let E epsilon, maybe E is already there. Okay. P epsilon, maybe. Just to, it is P epsilon equal to this projection 1 of this set. See, notice that if you have finitely many commuting things, then that's isomorphic to C of that, C of sigma E. C of sigma F or something. Okay. I mean, C of sigma S is isomorphic to C star algebra generated by x1 up to xk, right? We have already proved it. So now, and not just that, if you take L infinity also, there is a map. So you have a projection corresponding to this. One of all those T tilde, T1 up to Tk, such that Ti mod Ti minus lambda I is less than epsilon. Okay. I take this indicator function and then take the corresponding projection for this tuple. This makes sense. This is by that mapping. We have proved an isometric mapping from the L infinity of this sigma. I mean, there exists a measure on sigma, and the L infinity of this sigma to this. I mean, some into B of h. I mean, it's actually the Von-Neumann algebra, which I haven't stated. So it's actually will take. I mean, there's a corresponding projection which commutes with this. Okay. If you have problem, go and look at that proof. Okay, then P epsilon commutes with xi. Okay, I less than k greater than 1. And another thing is P epsilon is not equal to 0. The reason is this is an open set. Okay? This set T1 up to Tk, Ti minus lambda I less than epsilon. Okay. Yeah, so less than epsilon is open and intersects with sigma is non-empty. Okay. This set intersection sigma is non-empty. So it's actually an open set inside the spectrum, inside the giant spectrum. And for any open set inside the giant spectrum, see, we had this map. We have pi tilde from L infinity of sigma mu. Okay. Pi tilde is a map. Sorry, this is a map. To this B of h. Okay. Such that it will take single polynomial, superpolynomial, continuous function. But this is just an extension of this C sigma. Okay. C sigma is contained here. I mean, whatever. You can consider that as function, equivalence class plus function. And this is isometric. So that is also isometric. This, we proved that that's pi tilde is an isometric. Okay. Now this, you have a measure mu, and mu of that set U, you call it as U. Okay. Mu of U is strictly greater than 0. Because it's isometric on the continuous function. This has to be, I mean, if you have, I mean, it's non, see, every continuous function, the integral with respect to that is non-zero. So if you have an open set, then you can find an open bar. You can find a function which vanishes outside that open set and takes the value less than 1 inside U. Okay, and it's a positive function. And then that will show that the measure of this mu of U is greater than 0. Because that function should have what is the right reasoning, which is from Mu of u is, yeah, mu of u is greater than 0. Because there exists a continuous function, non-zero continuous function. There exists non-zero continuous f, not sorry, positive, not non-zero. Non-zero, non-negative. Okay. There exists non-zero is right. Non-zero continuous f. F is less than 1, greater than 0, and it vanishes outside U complement. That doesn't matter. By horizontal lemma, something. Okay, you will get something. I mean, so this is non-zero, and then this function should have. This function as an L infinity function, this is not a zero function, right? Because for L infinity is also is isometric. It's just contained in that. Okay? So because of this, mu of u should be greater than 0. This implies 1u is not equal to 0. This implies 1ut is not equal to 0. Is it okay? If it's not okay, tell me. The only point is mu of u is greater than 0. Okay, just convince yourself. Otherwise, we'll have a discussion class. We will have enough time. If you don't have a presentation, we'll certainly have a discussion class. So that time we'll discuss this if you have a problem. Okay. Okay. So now U is open, and its measure is not 0. So because of that, this P epsilon is not equal to 0. Okay. This P epsilon is not equal to 0. Now let x I epsilon equal to P epsilon times xi. So this is P epsilon commutes with xi and P epsilon xi. Okay. That's right. So now this accepts. Now we have lambda 1 up to lambda k, which is a joint eigenvector. What do you want to prove? We want to prove given any lambda 1 up to lambda k, in that we want to get using that we want to get this. Okay. Oh, that's okay. So now what nonsense? This is not correct. I'm sorry. We have to apply this P epsilon to xk plus 1. I'm sorry. Let you have xk plus 1. That's what we did last time. We did for the, I was mistaken by what we did from last time. So xk plus 1 epsilon equal to P epsilon xi. Now, because of Fuglet's theorem, this xi commutes with all x1 up to xn. So it will commute with spectral projection also, P epsilon also. So this also commutes with that. Okay. Sorry, xk plus 1. Xk plus 1. Xk plus 1 epsilon is P epsilon times xk plus 1. Okay. Okay. So now why should we choose? Why do we do that? It's not clear to me. So we will have 1 lambda k. K plus 1 is in the sigma of that. Then so we have lambda k plus 1 is in the sigma of xk plus 1. Okay. So this is implies, this implies lambda k plus 1 is in the spectrum of that also, right? So I'm sorry, we shouldn't have taken lambda k plus 1 there. I think we have to take, we have to choose lambda k plus 1 here. Sorry. Then it will work. I'm sorry, I have removed it. So I am not taking lambda k plus 1. Want a lambda k plus 1 in this. So here the statement is okay. Given lambda 1 up to lambda k in sigma f, we want a lambda 1 up to lambda k plus 1 in sigma e. Okay. And that lambda k plus 1 we choose here. Okay. Lambda choose. Now choose lambda k plus 1 in the sigma of xk plus 1 epsilon. Okay. Okay. Now by definition of this lambda k plus 1, there exists a vector x epsilon, okay, which is a unit vector, is in the range of 1u, whatever, range of p epsilon, that is 1u, precisely 1u, range of p epsilon, okay, with norm x epsilon equal to 1, and this xk plus 1 epsilon minus lambda k plus 1, this x of epsilon is less than epsilon, right? It's possible, such a thing is possible. But then we have already seen. On the other hand, xk, xi, there's no epsilon needed here. By definition, xi minus this lambda k x epsilon. I mean, because it is in the range, it satisfies. I mean, this projection is given by this function, no? So we have already done this. Okay, if you use that property of that function, precisely these vectors will satisfy this condition, okay, which we have already seen. You have to use the corresponding thing, t minus lambda k 1u. If you multiply by 1u, okay, then this will say this is greater than or equal to there is less than epsilon, no? This less than epsilon. So because of that, it will follow. That function is less than epsilon. So norm is less than epsilon. So because of it, it will follow. Anyway, we have already done this for the earlier thing. So it's an exercise. So this certainly will satisfy. Okay? Verify that. You apply for the write that property for the function, then apply the homomorphism to get the property for this. Okay? The xi will correspond to ti, and lambda k will be is lambda k, and you just you should use x, but you should have the property of that function, which will prove that the norm of this is less than this. So because of that, it will be less than epsilon. Okay? And this is a unit vector. X of epsilon is a unit vector. Okay, so this is true. So these things implies that this is a joint eigenvector. Okay, this x epsilon is a joint eigenvector. So lambda 1 up to lambda k.
It should be lambda I, right? Xi minus lambda I.
Xi minus lambda I.
Lambda I.
Yeah, sure. So lambda k is in sigma of E. Okay. Yes. So we have proved that PEF of sigma E equal to sigma F if E minus F is mod is 1. Okay. But then notice for any E1, E2, E3, okay, P of E1, E2, so you will project from E1 to E2, then you will project to E2 to E3 maybe. This is the same as P of E1, E3. You take this biggest set for E3 contained in E2 contained in E2. You take the big set E1, then project it on the smaller set E2. That means you are just picking up the coordinates which corresponds to E2. Then you go to E3, you are picking up the coordinate for E3. Directly you do this for E3, That's the same thing. Okay, so this is true. So because of this, you can do this. Because of this, you can prove it for if you have some. I mean, if mod of e minus f equal to some n plus 1. I mean, assume that it is true for all e minus f is equal to n plus 1. Then you can find a fn containing in V such that e minus fn equal to 1 and fn minus f equal to k, which is less than n, less than or equal to n. Okay? But then by induction hypothesis, you can assume for up to n, then you can prove it for n plus 1. I mean, you can apply this and prove this. Okay, and I think I don't have to give any more explanation. It's clear. Because of this, it's clear for any set. Okay, is it fine? If it's not fine, tell me when I write this definition. Is it okay? I'm just saying because of this property, which we have written. Okay, because of this property, not this property, the equality with the. Because of this property, okay, it follows that you can apply one projection at a time, and then I mean from sigma E1, you can when you project it, you get E2, and then project it, you get E3. Okay, and then if it is you by induction, you can assume it for when E minus F is n, you can assume it for that. When E minus n is n plus 1, for example, then you can project it on a set with the difference is 1, and then bring it to a set which is less than that. Okay, so it's clear. By induction, it's clear. Now the definition. Commuting self-adjoints. Okay, self-adjoints. Okay. Define sigma. You know sigma f. Okay, okay, let's define something before. Define sigma f. Okay. And this is contained in this direct product of sigma of xi equal to projection f inverse of sigma. Sigma f is a finite, I mean, it's in the finite tuple space, Rn, something. If n is the cardinality of f, then it is in Rn. Then you are taking the inverse image of into this sigma f. Okay. Okay. Then define sigma equal to intersection over all finite f. Take this intersection. We call this sigma, and this is what is called the joint spectrum of this family. So now the proposition. So 1, sigma is non-empty, compact. So it's a compact subset of this. Possibly it can be equal also at some cases, but it need not be equal. Even for 2 cases, it need not be equal. Okay, I mean, if the giant spectrum of some x1 and x2 is not same as sigma x1 plus sigma x2, you can get some examples. Okay. Okay. So the second thing is, so then there is this blah 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 spectral theorem which you already know. There exists a unique isomorphism or homomorphism. And because I'm going to specify the histology, it's isomorphism. pi. So this is a isometric isomorphism. So that exists. Isometric. By isomorphism, we mean star preserving homomorphism, which is unital and all those things. Okay, that's what we mean by homomorphism here in this class, in this course. So pi from C of this sigma to the C star algebra generated by xi. Such that the uniqueness comes from this property, pi of this projection. This projection corresponds to the singleton I, which will be just the Ti. Okay, if you have a triple to 1 up to Tn, then it's just the Ti, which is just the polynomial in one variable Ti. Okay? So that is equal to xi. The same statement which we prove for finitely many things, and it's a bigger statement for this. Should I write it for there exists a measure mu on sigma? I mean, let me not write it. I have done it several times now. So there exists a measure mu which is unique up to mutually absolute continuous, such that this continuous functional calculus is extended to pi tilde, such that whenever, which is also isometric isomorphism, and whenever some function fn converges to something in measure, then the corresponding pi tilde of fn converges to pi tilde of f strongly. And I mean, when fn is also uniformly bounded, something happens, which we have already said. Okay, so the same statement for whatever you I don't know how to write it. The proof is also same, so I don't have to. I will not write the proof also. Tell anything about the proof also. Okay. So the first thing is we already know this is a topological space. This is the direct product of sigma xi is a topological space. Okay, and so we are having some intersection, and all these things are. I mean, this sigma f is a closed set. Sigma f. I mean, this sigma f is closed. Okay, sigma f is closed. Closed subset of R mod this. Okay, so sigma f, which is just the inverse image of that. Okay, P or f inverse of sigma f. Okay, this is a continuous function. Coordinate functions are continuous function. When the topology is a product topology. Okay, with respect to the product topology, the coordinate projections are continuous function. So because of that, this is closed. Okay, this is inverse image of closed set. So this is closed, and that is just sigma is just the intersection of closed set. Sigma equal to sigma f. This intersection of closed set. Closed set. So this is closed. But the space is compact space. Okay, so because of that, so this is compact. This pi sigma is contained in this. This itself is compact, so this is compact. And sigma is non-empty because you project it onto any finite set, you get something which is non-empty, so it's non-empty. So these things are clear. So compactness. No. Well, we have to prove that. No, it's not clear. We project it onto something, we get something is for finite set. No, it's not for the infinite set. When we do for finitely many things, that is true. Okay, for infinite thing, you have to do to prove non-empty. So this I leave it as an assignment. I will tell you what to do. There is something messy, so I want you to do that. I mean, I can write it, but it's better you do that. Okay, so use finite intersection property. So we have proved it's compact. Okay. I mean, all these things, all these closed sets are compact sets. Sigma f is compact set. Okay, they are all compact set. So you have finite intersection property for this. For what? No, you have finite intersection property for the sigma fi, right? The bigger one. Okay. So you can take the closed subsets of something. So finite intersection, I mean, that is compact. This the whole topological space is compact. This is compact, right? So any collection of subsets will satisfy the finite intersection property. That is, you take the collection, if finitely many of them whose intersection is non-empty, then the intersection of everything is non-empty, right? So prove finite. So prove this is what you have to prove is show this has finite intersection property. Show this collection sigma of f fn. Then you will understand the projection. Okay, that's why f finite and has finite intersection property. FIP, I believe you understand what it means. It's finite intersection property. That is, you take finitely many of them, then the intersection is non-empty. Okay? You can use the earlier lemma, okay? And it is actually clear. You just have to write it. It's very few lines. See, the point is, if you take a bigger set, E, if you take the inverse of the projection onto the bigger set, you get the bigger set itself, right? And sigma f is contained in E, then the sigma E is contained in sigma f. Okay? And if you take finite, so if you take the, if f1 is one is included in the other, then it just the intersection is just the smaller one. Sorry, the bigger one. Okay? Anyway, think about it and prove that it has the finite intersection property. So then that will imply that sigma is compact. Okay? So, okay. So then that's all.
Yeah, but like won't it follow directly? Like because like product of sigma xi is compact, right?
What points are
Like product of sigma xi is compact, right?
correct? So
And this sigma is closed subset of compact set.
correct. So that then it's
Like
compact. That is clear. I'm proving it's non-empty.
oh right.
To prove it's non-empty, we are using the compactness.
Oh
Compact
right.
is if some collection has a finite intersection property, then the intersection of everything is non-empty. Okay, so sorry, I should have said sigma is non-empty. Sorry. What I wrote is correct. This assignment, this is assignment that shows that it has finite intersection property. Then it shows that this is non-empty. I mean, that is what I wanted to say. We have proved already compactness. We proved compact. It's closed subset of compact topological space, so it's compact. So it's non-empty or to prove. Okay? So it's non-empty because it satisfies the finite intersection property. Okay. So the second thing, there exists this isometric isomorphism and all that. So I mean, so there is one mistake in the book. Okay, it says the following. The book says this projection f, which are continuous function, okay, with f contained in I finite. The span of this is a total subset. They say span of this is dense by Stoneway tests. It says that this separates points. The span of this separates points in sigma. It says, but that is not true. You have to take polynomials in that. Okay, I mean this projection onto some f will only projection onto singleton f, for example, singleton some I or j. Okay, there where j is something. If you take projection onto that, projection will give, no? That's right. That will correspond to n polynomial. But you have to take the product. Projection f is not a function to complex numbers. No, it is a function to Rn. I don't know. Something in the book says which is, I don't think it's correct. It says the following. It says you take the projection f, but this is a function which takes values in Rn. Okay, but our C of sigma is a function which takes values in complex number. Okay, so we want functions there. So for that we can take fn, but I think he means the polynomial. So you take ti power n, which is the projection polynomial. This ti power These kind of things. I mean, the finite polynomials, it's just clear. In Ti1 up to Tin, okay? Where this I1 up to In is some subset of I. Okay? It separates points, or by Stone-Weierstrass, that is dense in C sigma. Okay? And if you assume the property of the theorem says that this pi of projection up to In, this is xi. Okay, this projection of I is just Ti. That is a polynomial corresponding to Ti, and that will go to this xi. Then the corresponding product will go to that, and we know that it preserves the norm. Okay, its norm. I mean, its norm as a function is same as. That we have proved for C of this, but this contained in that the norm is same as that. If you take the polynomial in T1 up to Tn, then the norm in sigma is same as norm in that. In those two. Okay, so it's okay. So it preserves the norm. So the function is pi naught or something, which you define on polynomials to this whatever this b of h, which is defined up to ti1 power n1 to tin power nk, ik power nk, which goes to xi1 power n1 to xik power nk. Okay, so this preserves the norm. Okay, this preserves the norm because the norm of this polynomial in that sigma as a function on sigma is same as the norm of the polynomial in this I tuple I1 up to in the just sigma I. Norm of the, okay, it's clear. But then we have already proved that preserves the norm. Should I write these things? I think it's clear. So because of that, anyway, tell me if you have a problem with this, whatever I'm saying. Want more explanation? It's clear, I thought. Is it okay?
Yeah, it's fine.
Yeah, it's fine for everyone, I believe. So one person says it's fine, I believe it's fine for everyone. Okay. So because of that, it preserves the norm. So it will they are dense and it will extend and view. It's the same thing we have already done 2 times or 3 times, I don't know. Okay, 3 times I believe. For Selford joint, then commuting family of Selford joint, then for normal. So we have already done it. So because of that, it's true. Okay, the same way, this is true. And the same way it is true for L infinity also. So it's done. And the other thing is, which I want to do is you write, there is an exercise given in Sundar's book. You write the whole thing for normal operators. Okay, it's just a translation of the statement using a lemma we have already proved. The lemma we have already proved, what it says is the following. If you take normal thing, you just have to write the whole thing. You can use the proof, whatever is proved here, and write the statement and the proof for normal operators. Okay, right? Or I just say it's just an exercise in Sundar's book. Exercise in this section. The statement is formulate and then do the same theorem. Commuting family of normal operators. It's fine.
Like arbitrary family, right? Not necessarily finite.
Arbitrary, commuting arbitrary family. Not so finite family. Anyway, any normal operator corresponds to 2 self-adjoint operators, 2 commuting self-adjoint operators. And sigma of those commuting self-adjoint operator, maybe x1 and x2, is same as sigma of t. Except that, if you identify this is an R2, this is in complex number, you just identify x1, x2 with x1 plus I. Okay, and that will follow for general commuting tuple also. So you just write it for this is the assignment. So I stop here. you tell me. So by next Monday, you tell me whether you want me to do the test class operators and other things, or you want to present these things. But then we have to find some 11 topics, which I can find. Some of them may be a bit more difficult. So we have how many more weeks? So let I will stop the recording and then